Hello and welcome to this video about vector space proofs. In this video we'll prove something about matrices in connection with vector spaces. We'll firstly define these two sets F and G to be bases of vector space V, and they both contain n vectors. And each vector in each of these sets can be written uniquely as a linear combination of the vectors in the other set. Here is an example. The jth vector in F can be written as a linear combination of the vectors in G, with these constants. The constants have two indices because we'll form a matrix from it later. And this is what the jth vector in set G is in terms of the vectors in set F. So I'll just write this equation up the top of the screen to show what a vector in set F is. And we can write this out as a system of linear equations for each vector in F in order from 1 to n. So we can pack up this system of equations into this matrix equation, and we can set matrix P to be equal to this matrix. And we can do a similar thing for matrix Q. So now we can state the theorem. It says that Q is the inverse of P. The statement of the theorem looks short, but we needed to define a lot of stuff, like to say what the matrices are. So now to start this proof, this is what each vector in set F is in terms of each vector in G, in compact sigma notation. And we can show what it is in dot notation here, to better follow it. So now we can manipulate this equation to be what each vector in F is in terms of every vector in F, because we've substituted what each vector in G is in terms of F into this equation. And so this is what it is written out in dot notation, and it looks very messy, with dots both inside and outside the brackets. So now we can manipulate this expression so that each vector in F is written as a linear combination of all of the vectors in F, including itself. And this is what it is in dot notation. Each vector in F has its own constant. And this is what it should be, since all of the vectors in F are linearly independent, because it's a basis. Then all of the constants will be 0, except for the constant in front of the jth vector in F, which will be 1. And we can write this in delta notation, this function being 0, except when the two indices are equal, and then it's equal to 1. And we can pack it up into sigma notation, with the coefficients being equal to the delta function. So I'll just write this equation up at the top of the screen. So each vector in F can be written like this in terms of the vectors in F, and also like this in terms of the vectors in F. This entry is the ijth entry in the matrix QP, and this entry is the ijth entry in the identity matrix. So we can write out this matrix equation like this. It follows that Q is the inverse of P, so we've proven this theorem fairly quickly, and without reference to past theorems, but using matrix notations. So I hope that you found this video to be helpful and educational. Please click like and subscribe if you did. Please write any helpful thoughts and ideas in the comments. Feel free to share this video, and thanks a lot for watching.